my four-step process is going away. And I don't think I need this anymore. Do I need this up here for you?
No.
Okay. So, what I really, really, really want to get at is this. I really want to get at this graph. Y equals e to the x. And we did this whole thing about y equals 2 to the x because e is kind of close to 2. All right, does anybody know what e is approximately? Anybody remember?
No.
2.7. Yeah, it's like 2.7182818284559. If you did that on your calculator, some of that would come up. It's definitely an irrational number. It's a very, very good number. Very good number. Do you remember why it's really, really good? Good, good. No? You don't remember? You know the guy, I did say, we have a story.
About it.
Yeah, it's called Euler's number.
Yeah.
E is Euler's number. Does that give you a hint?
I remember you telling us about that. I remember it was somebody's number. I just didn't remember what his name was.
Quiet, Emily. EU. Give me some words that start with EU.
Eugene.
Eugene, my dad. Yeah, very good man. Huh?
Eulogy.
A eulogy. And what do we do with a eulogy? We get up and talk trash about somebody or what? No, we get up and we say good things. What else?
Europe.
Europe. Very good place to go. Very good place to go. That's what we got?
Euro.
Euro.
Eureka!
There you
I don't
go.
know. Nothing?
No, EU's
It's not a very common letter for me.
Okay, well, we'll let you think about it. Come back tomorrow with a couple of words from me. Because last year we hit a lot of these words.
We did.
Yeah, we did. Okay, so we have y equals e to the x. And last year I gave you a numerical analysis of what e represented. Okay, we started off with this formula that says that the amount of money that you have in your account left over would be whatever principal you started with like 1 plus r over m to the nt. Do you remember that formula?
Yeah.
And then if you compounded continuously, this formula turned into p e to the rt. Remember that? The PERT thing, right? Okay. So this e idea comes into play with something in here. And we did a numerical analysis. We had this chart, and we let n get bigger and bigger and bigger and bigger and bigger. And our numbers became closer and closer and closer to about 2.7. And that was the numerical approximation for e, the limit as n approaches infinity. So we are looking at the end of the class period, right?
Yeah.
Okay. So this e, I want to give you another approximation of e. I want you to think of the graph of y equals 1 over x. Do we all know what that looks like in our heads? We should know what it looks like right off the top of your head. It goes through the point. 1, 1. Also goes through negative 1, negative 1. As the x's get bigger, my y's get smaller. And as the x's go closer and closer to 0 fractionally, my y's get bigger. Okay, so this function has a vertical asymptote and a horizontal asymptote. Right. I just want you to imagine, this is x equals 1. I want you to imagine the integral between 1 and something of 1 over x dx. And I want you to tell me when I would have an area bounded by this curve, the x-axis, a equals 1 and b equals something else, so that the area is exactly 1 squared unit. Now 1 squared unit looks like this. See this? 1 by 1 by 1? This is 1 squared unit. So if I chopped it right here at 2 and I shaded all this, do you think the region that I just shaded is the same as that 1 square unit?
No.
Not enough or too much?
Not enough.
Not enough. Do you think if I went all the way to 3, it would work?
Too much.
Too much. Okay? So this is like Baby Bear here. We got to go somewhere really just right. Okay?
About 2.7.
So it's about 2.7182818284559, otherwise known approximately as E. So when we go from 1 to E, then the area bounded in this region between y equals 1 over x, the x-axis, a equals 1 and a equals 2.71, b equals 2.71 approximately, we get an area of exactly 1. Okay? That's not happening. Okay, Ready, 1, 2, 3.
How